All right, well, good evening.
This meeting is being recorded.
Good evening, everyone, and welcome to today's third webinar in this four-part series called Yellowstone Perspectives, hosted by the Yellowstone Gateway Museum. This series, along with new museum exhibits, which will open over the next 2 summers, commemorate the 150th anniversary of Yellowstone National Park, the world's first national park. My name is Diane Chalfant, and I'm a volunteer and board member of the Yellowstone Gateway Museum here in Livingston, Montana. Our museum is a tremendous resource for our community, and so much of it can be accessed online. Beyond these webinar programs, the Yellowstone Gateway Museum also offers a fascinating digital photo archives, online exhibits, and research services. If you're not currently a member, we encourage you to become a member and explore more about the natural and cultural heritage of Park County, Montana. In a moment, I'll introduce the museum's curator, Karen Reinhardt, but first I'd like to go over a few housekeeping items so that you'll know how to participate in tonight's event. At any time during the webinar, you'll have the opportunity to ask questions of our presenter, Lisa Morgan. Your questions will be anonymous. To submit a question, just type it into the Q&A at the bottom of the control panel, and Karen and I will read the questions and share them with our speaker. As time allows, Lisa will address as many of the questions as she can after the presentation. We are recording this webinar and we'll upload it to Yellowstone Gateway Museum's YouTube channel after the event. On YouTube, you'll be able to watch the presentation again or direct the presentation to other people who might be interested in it. You could also watch some of our other fascinating online speaker series programs that we've presented over the last couple of years. And finally, following the webinar, you'll have the opportunity to take a very brief survey. We hope you will take this survey because it'll help us improve this series and other programs of the Yellowstone Gateway Museum. Now I'd like to introduce Yellowstone Gateway Museum's curator, Karen Reinhardt. Karen?
Thank you, Diane. Well, welcome everyone who's watching from home tonight. We hope that you'll register for the final Yellowstone Perspectives program next Wednesday, April 27th, presented by Katie Christensen, editor of the Artist's Field Guide to Yellowstone. She collaborated with 50 local artists and writers who paired up to reveal new ways of understanding the park's key species through prose, poetry, and artwork. Artists Jenny Lowe Anchor and DG House, and writers Elise Atchison, Todd Burrett, and myself will also participate. Now, to introduce tonight's speaker. Lisa Morgan earned a PhD in geology and geophysics from the University of Hawaii, where she specialized in physical volcanology. Lisa has an MS in geology from the University of Colorado, with an emphasis on volcanic stratigraphy, petrology, and rock magnetics. Her Bachelor of Science is in geology from the University of Missouri at Kansas City, with minors in mathematics and philosophy. Lisa's work in Yellowstone began in 1980, so 2022 is her 42nd year. She has also worked in other volcanic terrains like Japan, Mount St. Helens, Hawaii, Big Bend, and Costa Rica. Presently, her research with Yellowstone Volcano Observatory focuses on the geology and associated hazards in Yellowstone Lake. She and co-author Ken Pierce also track the Yellowstone hotspot along the 17 million years ago Snake River Plain, Yellowstone Plateau volcanic province. From 1999 to 2004, Morgan with colleagues mapped the floor of Yellowstone Lake, becoming the first to recognize the complex geology present and active on the floor of Yellowstone Lake today. Please welcome Lisa Morgan. Okay, Lisa, take it away.
Well, hi. Okay. So tonight, good evening. I hope everyone's well. I'm Lisa Morgan, and the title of my talk tonight is The Dynamic Floor of Yellowstone Lake, the last 14,000 years of hydrothermal explosions, venting, doming, and faulting. The image you see on the screen is an oblique colored bathymetric map of Yellowstone Lake. And we're looking from the south near the promontory north into the lake. For those of you not familiar with the term bathymetric, you can think of it as the equivalent to underwater topography. Here, the colors in red represent shallow areas in the lake, and the colors transition to blue and purple, representing the deepest parts of the lake. I'm going to talk about several features, which I will point out right now during my presentation. Here's part of the margin of the Yellowstone caldera coming through here. This is Frank Island, Dot Island, Stevenson Island. We'll be talking about the deep hole, Elliott's crater, a large explosion crater, Mary Bay explosion crater, and we'll be talking about hydrothermal domes that are also in the lake. So let's go. So, oh, here we go. So this is a paper that has recently been accepted for publication by the Geological Society of America Bulletin. And I had many other scientists contribute to this incredible effort, including Pat Shanks, who contributed significantly to this work, and Ken Pierce and others. It's a group of scientists from many institutions and universities. Our funding was provided by the National Science Foundation with support from the U.S. Geological Survey, the Global Foundation for Ocean Exploration, Woods Hole, Oceanographic Institute, and Yellowstone National Park. So here's a map of Yellowstone National Park outlined in orange here, showing a simplified geologic map of Yellowstone National Park. The two features I want to bring your attention to for the purposes of tonight's presentation is Yellowstone Lake, shown in yellow here, which straddles the southeast margin of the 631,000-year-old Yellowstone caldera. So in this study, we collected piston cores from Yellowstone Lake, and the image on the left is a Kuhlenberg coring platform from the University of Minnesota Twin Cities and its Continental Scientific Drilling Facility. This Kuhlenberg platform has core barrels that are up to 12 meters in length and are lined, these metal core barrels are lined with polycarbonate liners. It collects a continuous sedimentary core. The image on the right is the core collected from, I think, the deep hole after the polycarbonate liner has been extruded from the core barrel and then been sectioned into 1.5 meter or less sections and then labeled appropriately. We applied a whole black bag of tools to this study, and I want to emphasize this is the first analyses of subaqueous or underwater hydrothermal explosion deposits. So we're basically unraveling a puzzle that no one's done before. There were a lot of surprises and a lot of learning. Oops. Oops. So this is a map of the large bathymetric map of Yellowstone Lake, showing our piston coring sites in Yellowstone Lake, shown in bright pink stars. And we collected 2 in Cub Creek Pond, 4 kilometers east of Yellowstone Lake. Also shown on this bathymetric map are the topographic margin of the Yellowstone caldera, the Eagle Bay Lake Hotel Graben fault zone, and large hydrothermal explosions, craters, Turbid Lake on the northeast side of the lake, Indian Pond just north of the lake, the Mary Bay crater in and out of the lake, Elliott's crater, Duck Lake, Evil Twin, and there's other craters, explosion craters in the lake. The inset in the map is a heat flow map of the northern part of Yellowstone Lake, where the red color represents high areas of high heat flow values, and the blue represents areas of low heat flow values or cooler parts. So the hottest part of the lake is right here in the northeastern part. I created on the right, you see a cross section of the topography or the bathymetry going through the various cores we collected in 2016. So we collected cores from the Lake Hotel Graben, an inactive dome, deep core, and the main point, deep hole, main point of this is to show what pretty dramatic relief there is on the lake floor, and that we have a lot of geologic activity. So our targets in 2016, which is the main part that was funded by NSF, is inactive hydrothermal dome north of the active North Basin hydrothermal dome, and seismic reflection profiles and bathymetry show doming of lake sediments. The second target was the Lake Hotel Graben, and we have active faulting there. And for those of you who aren't familiar with the term graben, it refers to a double-sided fault where the area between the two faults is subsiding. The third area that we collected in 2016 is the deep hole. And it's a active 200-meter wide hydrothermal vent field. And it is the deepest part of Yellowstone Lake at just over 119 meters. It's at the southeast end of a set of active northwest trending fractures filled with dozens of hydrothermal vent fields. Seismic, and here's a profile A to A prime across the deep hole, showing the dramatic relief that's present in the deep hole. On this, we have over 40 meters of relief, so pretty steep. The seismic reflection profile shown here shows an active 6.7 meter fault, or a fault with an active fault with 6 meters of offset on it. We have ascending hydrothermal fluids that are pushing up altered lake sediments into dome shapes. The fourth site was the Elliott's crater, which was discovered only in 1999. And we cored two cores there. And then off to the southeast, we cored in the quiet Central Basin for our fifth site. This is a seismic reflection profile from north to south of Elliott's crater and the deep Central Basin. There's about 70, 80 meters of difference in elevation between the south crater rim and the floor of Yellowstone Lake in the Central Basin. And then our sixth site was on the steep eastern shore of Yellowstone Lake in an area that we could tell in our seismic reflection profiles was prone to mud slumps. So this is a geologic map of Yellowstone Lake. And the main thing I want to show is that the northern half of Yellowstone Lake is within the southeast portion of the Yellowstone caldera. And here's the Yellowstone caldera, the topographic margin of it. And you can see that and this area is prone to high seismicity and subject to active deformation of the Yellowstone caldera. We have active hydrothermal vent fields shown in blue. We have large hydrothermal explosion craters in the lake. We have hydrothermal domes in this area, landslides coming off of steep slopes, and post-caldera rhyolitic lava flows shown in pink. So this diagram is a summary of the cores from Yellowstone Lake and region. And just to get yourself situated, the vertical axis is the depth in the core in meters. And the horizontal axis is the grain size as noted in the explosion deposits, going from the finest clay to coarse pebble. We have two tephras in the cores, and they're the 7,600-year-old Mazama ash, which came from the eruption of Mount Mazama in Oregon, which formed Crater Lake, as you may be more familiar with it. We have the older 13.6 thousand-year-old Glacier Peak ash from Washington. And these tephras are noted as MZ for Mazama and a bold line, or GP for Glacier Peak and a less bold line. We also have multiple hydrothermal explosions in the cores. And what we noted is that we have two very large hydrothermal explosion events. We have one that we refer to as Elliott's crater, which exploded at 8,000 years ago and is in the magenta color. And we have the Mary Bay explosion deposit, which formed at 13,000 years ago and is shown in blue. You'll note that the Elliott's crater explosion deposit is below the Mazama ash, and the Mary Bay explosion deposit is above the Glacier Peak ash. We also identified 14 small explosion events noted in gray here. And well, we have large explosion craters, other large explosion craters in and near Yellowstone Lake. None of their deposits were identified in these cores. If you look at YL162C, we can see active process of faulting occurring in this graben. And if you note where the MZ is at 9.3 meters, this is about 1.3 meters below the average 8-meter depth of Mazama in the northern lake. So there's a lot of subsidence that's gone on since Mazama has been deposited. Likewise, if you look at YL161A, the dome, you will note that the Glacier Peak ash, a 13.6 thousand-year-old ash, is at 2 meters, a little less than 2 meters. And this is about 8 to 10 meters above its average depth. So in the northern lake. So there's been a lot of uplift on this currently inactive dome. So we wanted to make a chronologic assessment of what was in the cores, how old were the ashes or the tephras, and how old were the lake sediments and the explosion deposits. And so using tephra chemistry, we were able to identify and distinguish the Mazama ash, noted here in black stars. And the filled black stars are from our core samples. And from the Glacier Peak ash in the black boxes, squares. And these are distinct from Yellowstone reworked ashes shown in diamonds. In the figure on the right, we have depth in core versus the radiocarbon age calibrated in thousands of years before present. And we were able to develop a linear regression analysis for that helped us determine what the sedimentation rates were in the lake. And so in the Northern Lake and in the West Thumb Basin, we determined the average sedimentation rate was 1.06 meters per 1,000 years. And in the Southern Lake was 0.62 meters per 1,000 years. So this is a diagram where we looked at selected chemical and physical characteristics of the sublacustrine hydrothermal explosion deposits. Again, the vertical axis is depth, and on the horizontal axis, we show magnetic susceptibility represented with the MS, strontium, arsenic, and silica. And these are relative abundances of these various elements. And what we noted is that in all of the hydrothermal explosion deposits, they are depleted in arsenic, enriched in strontium, enriched in silica, and there's an increase in silica associated with the finer grain size. And we have high values of magnetic susceptibility. So you can see this very clearly in this particular hole. We show the Mazama ash, noted as MZ, the Glacier Peak ash, noted as GP, the Elliott's explosion deposit, noted in pink or magenta, and the Mary Bay explosion deposit, noted in blue, and the other hydrothermal explosion deposits as HE. And these are in holes YL163A, YL165A, and YL923A. So this is an example. Let's zoom in on one of these hydrothermal explosion deposits in one of the cores. And this is a core YL162C from the Lake Hotel Graben. And on your right is toward the bottom of the core. It's on its side. And as you go to your left, you go up upwards into the core. This is a 7-centimeter deposit, explosion deposit from Elliott's crater. And you can see the density is higher, has higher values. Magnetic susceptibility is higher. The arsenic is depleted. The strontium is really enriched. And this is all relative to unaltered lake sediments. Right here over with this white line, but you can kind of see there's a 5 millimeter thick ash layer of the Mazama ash. Oh, and also you will note that the explosion deposit, this is its base, is normally graded, and it's coarser grained at the base, and it grades upward to finer grained. This is another example. Again, we're looking at a core from the bottom on the right to the top on the left. And we're looking at about a 1.6 meter section of Elliott's crater deposit. And again, we have depletion of arsenic in the explosion crater deposit relative to the unaltered lake sediments, and enrichment of strontium in the explosion deposit relative to the unaltered lake sediments. One of the things we noted is that we could identify multiple explosion events within the Elliott's crater deposit. We can also see this in the Mary Bay explosion deposit, but I'm showing the Elliott's crater explosion deposit here. We also noted there were an abundance of white fragments, which are chloride rich, should be chloride rich muds in the explosion deposit, especially in the lower sections. On the diagram on the left, you'll note we have in pink 3 more locally sourced hydrothermal explosion deposits higher up in the core. And the source for these particular local explosions is assumed to be the deep hole, a vapor-dominated vent field. So all of these are examples of what subaqueous hydrothermal explosion deposits look like. And you might say to yourself, wow, these all look really different. And they do, but they all have the same signature of high enrichment in strontium, depletion in arsenic, enrichment in silica, and high values of magnetic susceptibility and density. So we tried to create a framework by creating a facies model for these subaqueous hydrothermal explosion deposits. And we were able to categorize them into kind of 6 different facies that we interpret as primary fault explosion deposits, where we have large and heavy drop stones that have are at the base of these deposits. Some of those drop stones are smaller, but the point is these drop stones are bigger than the sediments that they're in. And that's because they're heavier and they could fall through the water column faster, and in some cases actually impact the lower lying lake sediments. We note that these primary fall hydrothermal explosion deposits, we subdivided into 2 facies that were coarse breccias and fine breccias. The coarse breccias are proximal or close to the vent, and the fine breccias are distal or far from the vent, or represent waning phases of the explosion. We then also noticed that some of these deposits had channels cut into the lower sediments, and we interpreted those as remobilized primary fall deposits that were redeposited due to being deposited in areas of high relief. And so we have the coarse ones that are very close to source, and we have fine ones that are farther from source, or in terms of the material that came out. We also noted that in the area where we cored, where we on the eastern shore, steep shoreline of the lake, where we had identified landslide or mud slump deposits, we noted that in the deposit that identified with the characteristics of other hydrothermal explosion deposits, the high enriched strontium, depleted arsenic, high silica, high values of magnetic susceptibility, we identified these different chaotic blocks of mud with black sulfitic streaks, and they had these class of chloride-rich clay. Chloride-rich clay. Okay, and then between, I noted that we could identify multiple events in these hydrothermal explosion deposits. And between these events, we identified very fine-grained, massive mud deposits that had weakly developed beds. And we interpret these as suspension fallout deposits, which were the very fine material left suspended in the water column that settled out after the main deposit was emplaced. So to have a look at the 8,000-year Elliott's crater explosion deposit, you can see they're well sorted, and they're normally graded. The Elliott's crater was first discovered in 1999 in high-resolution multi-beam echo sound mapping of Yellowstone Lake. The deposit from Elliott's crater is found only in the lake cores. So far, no exposures have been identified on the land. And the Elliott's crater deposit is characterized with an abundance of this white chloride-rich clay class, which are inferred to be from the caprock of a pre-explosion hydrothermal dome. So you can see the drop stones. We have a large 2.5 centimeter diameter rhyolite class at the base of this particular explosion deposit. And you can see in this and this deposit, D and E, you can see kind of alternating coarser and finer, coarser, finer, coarser, finer. And these we think represent pulsations in the explosion column. Okay, this is another example of a deposit from Elliott's crater. And in this case, this is core YL164C, and we cored directly into Elliott's hydrothermal explosion crater. And we found over 3.7 meters of explosion debris. Much of it is primary fall or fallback material from the explosion column. And you'll note this looks really different from the other hydrothermal explosion deposits, but it's the same thing. And you'll see that there's these white fragments of hydrothermally altered chlorite, illite, framboidal pyrite, and anhydrite dispersed throughout the cores, and they become much larger with depth. This is 5 to 6 centimeters in diameter. And some of these fragments look similar to volcanic fiamme that we see with pumice in volcanic deposits. The 13,000-year-old Mary Bay explosion deposit, we find these deposits on land and in the lake cores. But the deposits present in the cores are very distinct from those found on land. Those in the cores, shown here on the left, are well sorted, they're finer, and they're normally graded. And it all indications that they were subaqueously deposited. Those on land, as shown here in the lower right corner of the figure, are very poorly sorted and are very coarse. Immediately below the Mary Bay breccia deposit, almost everywhere, you see this bedded fine sand and silt deposit. And we see a similar type deposit in the cores. And we interpret this deposit as to be from a tsunami event. And this is a large class of this bedded fine sand and silt deposit. It's 8 meters long, and it's been incorporated into the Mary Bay explosion deposit. Fractures are also associated with the Mary Bay deposit, and we see these large fractures, 1 to 1.5, 2 meters in length, and up to tens of centimeters wide, that are filled with hydrothermal explosion breccia from the Mary Bay explosion event. These 2 images are from near, just right outside. They're onshore. They're just outside the crater rim, 1 to 1.5 kilometers away from the rim. And in a core from between Dot and Frank Island, we found this fracture as well as some other fractures above that are filled with hydrothermal explosion material we think is Mary Bay. And this is above the glacier peak ash, and it's below the Mary Bay explosion deposit in what was then very soft sediment. And this particular core is 13.7 kilometers from Mary Bay crater. Hydrothermal fluids in Yellowstone Lake have 2 very different chemistries. We have alkaline chloride fluids and vapor-dominated fluids. And in this diagram, showing temperature in centigrade versus log of activity of silica, aqueous silica, we note the alkaline chloride fluid field in dark gray and the vapor-dominated fluid in light gray. And alkaline chloride fluids produce neutral to alkaline pH, sodium chloride rich, high chloride fluids, and flash to steam during hydrothermal explosions, producing more strongly explosive events than those produced by vapor-dominated fluids. On this diagram, we show the quartz saturated line, where on the right side of that line, the field is quartz saturated. On the left, it's undersaturated. And we also show the amorphous silica saturated line. Same thing on the right, it's saturated. On the left, it's undersaturated with respect to amorphous silica. These alkaline chloride fluids produce alteration dominated by silica and chloride. Here we see daphnite and chamosite, and smectite. Here we have beetalite and saponite, and that's it. Then examples of these can be found in the upper, midway, and lower geyser basins. The vapor-dominated liquids are rich in water, CO2, and H2S, and they produce acidic, low chloride fluids. Simple vapor expansion produces smaller, possibly more frequent explosive events. Vapor-dominated fluids produce alteration dominated by kaolinite, as shown in this diagram. A good example of these can be seen at the Mud Volcano Thermal Basin. So these images are petrographic images from smear sites of sediments from the hydrothermal explosion deposits found in the Yellowstone Lake cores. And 2 points I want to make is that, one, the influences of hydrothermal fluids and subsequent hydrothermal alteration are very apparent in the sediments. And here you can see a zoned feldspar with secondary hydrothermal quartz growing around it. In the figure in the upper right corner, we have dark, or the black, amorphous, framboidal pyrite. And in this particular case, it's encased in a fragment of silicified filamentous bacteria. Hydrothermally altered actinolite is also present, and it's an altered amphibole. And on the edges of this actinolite, you can see these things we call denticles, which are basically leached edges that of the crystal along cleavage planes. The second point I want to make is that in these sediments, the impacts of the hydrothermal explosions also are very apparent. Many of the minerals and fragments, grains, have chattered edges, like this quartz grain shown in the lower left figure. And we also, in both the Elliott's crater and Mary Bay explosion deposits, we find ample fragments, a lot of concentrations of rhyolite, which indicate the excavation of unmapped rhyolitic lava flows at depth. So we also collected a bunch of short cores, something like 27 short cores. And these are generally less than a meter deep. And the points I want to show here, of 3 of these, we identified what we interpret as hydrothermal explosion deposits. They look like hydrothermal explosion deposits. They're normally graded. They're well sorted. They have the signature of hydrothermal explosion deposits with high values of magnetic susceptibility, enrichment in strontium, depletion in arsenic, enrichment in silica, especially in the finer grained parts of this. These deposits are at depths between 11 and 36 centimeters from the floor, below the floor of the lake. And based on average sedimentation rates for the northern lake, these explosions occurred roughly 160 to 360 years ago. So very recently in geologic time, and represent ongoing hydrothermal explosion activity in Yellowstone Lake. We also looked at a couple of seismic reflection profiles, one from the Lake Hotel Graben in the northern lake, and one from the Eagle Bay Fault Zone between Snipe Point and Frank Island in the southern part of the lake. Based on sedimentation rate within the Lake Hotel Graben, which is higher than outside of the Lake Hotel Graben at 1.2 meters per 1,000 years, we can identify, and these are faults, and they're offsetting these horizontal layers, which are the lacustrine sediments, and we can identify reflectors in the seismic reflection profile. And reflector D represents deposition about 8,000 years ago. Reflector E represents deposition at about 13,000 years ago. The total displacement of D is only about 15 centimeters, whereas the total displacement of E at 13,000 years ago is 1 meter, about 1 meter. Looking at the southern area where the seismic reflection profile was collected, and based on sedimentation rate for the southern lake at 0.62 meters per 1,000 years, reflector C represents deposition at about 8,000 years ago, and reflector D represents deposition at about 13,000 years ago. You'll note these vertical lines represent faults, and you can see that there's been a lot of displacement, especially at 8,000 years ago, where we estimate the displacement was about 2.8 meters, and the displacement at 13,000 years ago was about 0.7 meters, or pretty close to what we see in the Lake Hotel Graben. The event at 8,000 years was more focused in the southern lake on the Eagle Bay Fault, whereas the event at 13,000 years ago was distributed over the 25 to 30 kilometer length of the lake along the Eagle Bay Lake Hotel Fault Zone. Both events contributed to triggering hydrothermal explosions at Mary Bay and Elliott's crater. So this is a schematic representation of a large hydrothermal explosion in Yellowstone Lake. In Yellowstone, hydrothermal explosions occur in areas where the rock has been affected by extensive, long-lived hydrothermal alteration. In these deposits, everything is hydrothermally altered. The class and the matrix are extensively hydrothermally altered. There is no fresh material. The large hydrothermal explosions are triggered by a sudden drop in pressure at the surface, which allows the alkaline chloride liquids that are at or near the boiling point to flash to steam. And when you have this phase transition from liquid to steam, you get a 1,600-fold increase in volume. The pressure drop is transmitted through hydraulically connected fractures and starting a series of continuous and cascading explosions of fractured rock, boiling mud, altered clay, hot water, and steam. The explosion continues downward until the system literally runs out of steam. And this is these rock units over here. This is a subsurface diagram of lithologies that we interpret below Mary Bay. And we have beach sands and gravels, deep lake sediments, glacial lacustrine sediments, and we have this rhyolitic lava flow. So this is a map showing the aerial distribution in magenta on the left, in blue on the right, and thickness in centimeters. These numbers are like 5 centimeters, 2 centimeters, the thickness of the hydrothermal explosion deposits. The estimated volume of the deposit from the Elliott's crater explosion event is 0.082 cubic kilometers. The explosive energy from the Elliott's crater event is estimated at 9.84 times 10 to the 14th joules. The estimated volume of the deposit from the Mary Bay explosion event is 0.268 cubic kilometers, and is 3 times larger than the Elliott's crater deposit. The explosive energy from the Mary Bay event is estimated at 3.21 times 10 to the 15 joules. So what does this compare to? And so we looked at what the explosive energy from the Hiroshima atomic bomb was, and that's 6 times 10 to the 13th joules. So both Mary Bay and Elliott's crater were much more put out much larger explosive energy than the Hiroshima atomic bomb. In comparison to some large volcanic eruptions, such as the 1882 Krakatoa eruption in Indonesia, which was 13,000 times that of the Hiroshima bomb, and Mount St. Helens in 1980, which is 1,600 times the Hiroshima bomb. These volcanic eruptions are far bigger than the hydrothermal explosions, but these large hydrothermal explosions in Yellowstone put out a lot of explosive energy. I thought it was kind of cool, much bigger than the Hiroshima bomb. So this is an image from a paper by Ken Pierce and others in 2007. And it's a LiDAR map of Yellowstone River from its outlet at Fishing Bridge to Lahardy's Rapids. Ken was able to map various lake terraces that date back to 14 to 14,500 years ago. And here's the ages of these various lake terraces that he mapped. And these are depths of the lake level above present. So at 14 to 14,500 years ago, S6, the lake was all the way up to Lahardy's Rapid, as shown by this dotted line. And at 13.6, it was here as shown in the S55. So Yellowstone Lake occupied this part of the outlet. And these shorelines, the S6 and S55, indicate a much higher lake level prior to 13,000 years ago when Mary Bay explosion event occurred. One of the things that was really unusual in this project and in mapping the Mary Bay explosion deposit was that I noticed that the explosion deposit on land was very different than that in the cores. On land, it's coarse, it's poorly sorted, and it was deposited in a subaerial setting. So water could not have been where the at that time. And the cores are very fine and normally graded and well sorted and very indicative of being deposited in a subaqueous environment. We suggest that these observations indicate that the lake level dropped rapidly about 14 meters to within a few meters of the present day lake level for a short period of time during the Mary Bay hydrothermal explosion. We hypothesized that the lake level drop resulted from the rapid erosion of glacial deposits in the outlet channel at Lahardy's Rapids, resulting in a major outburst flood. So this is a diagram showing summary of our events as recorded in the sedimentary cores from Yellowstone Lake. So I'm just talking pretty much about what we see in the cores. And here you see the sequence, and we have age of the event and on the x-axis and relative magnitude of the event and the y-axis. And we have Pinedale ice sheet was melting and receding 14.5 to 15,000 years ago. The Glacier Peak ash was deposited in an ice-free lake at 13.6 thousand years ago. Then we have the sequence of events where we have a very large seismic event, maybe a magnitude 6.5 earthquake. Then this was followed by a tsunami event, which deposited these fine bedded sand and silt deposits. Then we had the lake outburst flood, and then we had the explosion of Mary Bay. We note that there are at least 16 hydrothermal events of various magnitudes in the cores, and 14 of them are minor explosions. Most of these are probably from vapor-dominated fluids, and 2 very large hydrothermal explosions, which were dominated by alkaline chloride fluids. The ages of the explosion events range from 13,000 years ago to as recently as 1860 CE. The 2 extensive and large volume hydrothermal explosion deposits are present in 14 of the 18 cores, and several other large explosion craters, as I've said, are in and peripheral to the lake, but we didn't find their deposits. And so this suggests that some of these explosions have a lateral or a directional blast component associated with them. The Elliott's crater explosion event was associated with a major seismic event at 8,000 years ago, and we suggest that it ruptured an impervious hydrothermal dome, and that the light gray to white chlorite-rich clasts are remnants of that cap rock on the hydrothermal dome. The Mary Bay explosion was triggered by a sudden and significant 14-meter drop in lake level, which was stimulated by a 13,000 year seismic event 13,000 years ago, followed by a tsunami, and then outlet channel erosion at Lahartie's Rapids. Elliott's crater and Mary Bay explosions are 2 of the largest hydrothermal explosions in the world. In fact, Mary Bay is the largest, Elliott's is the 3rd largest, Turbid Lake is the 2nd largest, and they have 16 to 54 times greater explosive energy than that released by the atomic bomb dropped on Hiroshima. So we can rank volcanic, hydrothermal, and earthquake hazards in Yellowstone. And the 2 biggest hazards right now in Yellowstone are considered from strong earthquakes and large hydrothermal explosion craters. This is a diagram showing frequency and level of destructiveness. So we have small hydrothermal explosions, which we might have several to many per century. Recent calculations show that the most recent small hydrothermal explosions occur 1 every 2 years, and the large hydrothermal explosions seem to occur 1 every 1,000 years, or maybe a little bit less than that. So hydrothermal explosion craters in Yellowstone National Park are the largest in the world. This diagram shows diameter in meters, all at the same scale. And this is from Brown and Lawless's 2001 paper showing the diameter of hydrothermal explosion craters in New Zealand and worldwide. And most of these are less than 200 meters in diameter. There's a few that push up to about 500 meters. But if you compare these with different explosion craters in Yellowstone, they pale in comparison to those in Yellowstone. Most of the large hydrothermal explosion craters in Yellowstone are greater than 500 meters in diameter. And the material in the explosion debris is hydrothermally altered, suggesting a source from an established, long-lived, and extensive hydrothermal activity prior to the explosion event. So where in Yellowstone do you find this kind of alteration happening? Well, you find it in the thermal basins. And so I plotted here the diameters of thermal basins in Yellowstone National Park, And these thermal basins today have similar dimensions to large hydrothermal explosion craters. So I asked the question, do large hydrothermal explosion craters represent former thermal basins? And I'll leave you with this aerial photograph. I think we got this from Yellowstone Forever, but it's of Excelsior explosion crater, which exploded in the late 1880s and was witnessed by Superintendent Norris. We also see Turquoise Lake and Opal Lake, and of course, Grand Prismatic. And I'll finish with, could all of these features be large or hydrothermal explosion craters? That's it. Thank you.
Wow, that was really interesting and exciting question you left us with at the end there, Lisa.
Wait, I have to turn on my light. It got dark.
Okay, so we're gonna open it up to questions. We're gonna remind our audience that if you have a question, just type it in the Q&A at the bottom of the screen, and we'll present them to Lisa and you know, look forward to the responses. So Lisa, I have a question for you. You know, whenever you think of Yellowstone, you do think of New Zealand and the similar hydrothermal features and so forth. Since you started working in Yellowstone Lake in the late 90s, and you opened up by talking about how you pioneered these methods for studying these hydrothermal craters and features underwater, are there other places in the world, whether it's ocean or lakes, that have used the methods that you developed?
Well, yes and no. It depends which techniques, and it depends what has been done. So Lake Taupo has certainly been mapped with high resolution, multi-beam, echo sound, sonar mapping, and has created some really nice bathymetric maps of Lake Taupo. Another one is Lake Rotorua in New Zealand, and they've done a lot of work there. I think, I'm trying to think of it. Well, I don't think they mapped it. I'm trying, Lac de Mer in Chile is another location where I don't think they've done bathymetric mapping, but they've done seismic reflection profiling. And they've done seismic reflection profiling as well in Lake Taupo and Lake Rotorua in New Zealand. What's unique about this study is I don't know of any deep cores that have collected or identified hydrothermal explosion deposits that were deposited through the water column.
Oh.
And so I've studied the hydrothermal explosion deposits in Yellowstone on land for 20 years or so. And the ones in the lake are very, very different than what we see on land. And so the study was kind of difficult because I had no resource to go to. I had no reference to go to say, well, what do other hydrothermal explosion deposits that have traveled through a water column look like? So this was a real puzzle trying to figure all of this out, and it was painstaking, and it took quite some time. I think we've had a real opportunity in Yellowstone where we've had a lot of interest and funding from the USGS, from the National Park Service, specifically Yellowstone National Park, from the Yellowstone Foundation, now Yellowstone Forever, from other organizations, private foundations such as the Global Exploration for, what is it? Global Institute for Ocean Exploration, Woods Hole Oceanographic Institute. And so Yellowstone has gotten a lot of funding and interest. And so we've been able to really bring lots of disciplines together and not only figured out the hydrothermal history of the lake, but also, and I didn't discuss this at all, but also the climate history of Yellowstone Lake and the seismic. We've done all kinds of seismic profiling where we can look at rising hydrothermal plumes from the vents. So we've really, in our most recent project funded by the National Science Foundation, which is referred to as called the Hydrothermal Dynamics of Yellowstone Lake, we brought all of these disciplines together from a huge variety of universities and institutions. So it's been truly a real collaborative effort. And when I didn't know something, I went to somebody and asked them.
Well, the questions are coming in. I'll turn it over to Karen if, and looks like you're still muted, Karen. There.
Okay, Lisa, yes, we do have some more questions. Here's the next one. How does the Huckleberry event fit with the sedimentology?
The caldera forming event fit with the lake sediment, or
I guess so. I'm not sure.
Well, in another recent paper that we did, I think we published it in 2020, and the first author is Claire Boulagon. We did a magnetic survey of the northern part of Yellowstone Lake, and we combined it with previous magnetic surveys. And we looked at heat flow and other data sets. And we think, and this isn't the first time to be noted, but we think an edge of the Huckleberry Ridge caldera goes through the kind of western main side of the Yellowstone Lake. But in terms, but that's all that I can say in terms of the lake and its relationship to the Huckleberry caldera. If I could go back to one of my first slides, if that's okay, I'll note on this generalized map of Yellowstone, I noted the Yellowstone, the topographic boundary of the Yellowstone caldera, and the topographic boundary here is of the Huckleberry Ridge caldera.
And you'd have to share your screen.
Oh, sorry. Hey, I'm having to multitask. Okay, can you see it?
Yep.
Okay, so in this generalized map, I show the Yellowstone caldera topographic boundary. And in this is also shown the topographic boundary of what's assumed to be the Huckleberry Ridge caldera. And while that erupted 2.1 million years ago, and while I don't show it here, we would take this boundary of the Huckleberry Ridge caldera and bring it through Flat Mountain Arm and then bring it up along the western side of Yellowstone Lake. And so that's as much as I can say about the relationship of Yellowstone Lake and the Huckleberry Ridge event.
So Lisa, earlier when you were describing it was fascinating looking at the map and looking at Lahardy's Rapids and imagining the lake levels changing. This person asks about that, and they want to know the cause of the pressure drops that triggered the hydrothermal explosions. And also, well, they say, is it seismic? Or were you saying that the lake outburst flood dropped the lake level, which reduced pressure? And they just want
Yes.
you to kind of explain the sequence of the for the outburst flood.
Yeah, I mean, there's, we think there is seismicity associated with both the Mary Bay and Elliott's craters events, but it's not the only factor. And so we think that this lake long seismic event that is associated with the Mary Bay event, that it started a series of events that triggered a tsunami event. That tsunami deposited sand onshore and was left suspended sediments in the lake, which we can find at the base of the Mary Bay explosion deposit. And then we think that this tsunami event, you know, there was so much water that was channeled up from Fishing Bridge to the lake outlet at Lahardy Rapids. And at Lahardy's Rapids, for those who know the geology there, to the west of Lahardy's Rapids, we have hard rhyolitic lava flows that are present on Elephant Back Mountain. And to the east of Lahardy's Rapids, we have Sour Creek Dome, which is composed of very hard lava creek tuff. And so you have these softer, less resistant glacial deposits that are deposited between these two hard rocks. And we think that there may have been some kind of a dam, glacial rock dam that was at the Lahardy's Rapids, and that this force and push and rise of water in this narrow channel created this channel erosion that caused the outburst flood.
Okay.
So, and in the Elliott's crater explosion, we think that, as shown in another one of my diagrams of this, I'll go back. First, I'll share my screen. Okay. Share. And now I'll go to this cross section. And if you look at this, where Elliott's crater is, we think was a remnant hydrothermal dome. So while we think there was a significant seismic event associated with triggering the Elliott's crater explosion, we think what happened is that this dome was capped with impervious clay, chloride-rich clay. And we've sampled this from other domes in the lake. And we think that this dome failed. And so it was that failure triggered by the seismic activity that caused the sudden drop in pressure that caused the explosion.
Great.
Thank you, Lisa. There's another question here. Is there ongoing activity on the lake floor? And if you could describe some of that activity that maybe you noted when you were out surveying the lake.
Oh, yeah. It's a very active lake. I have a paper, I think we published it in 2003, the floor of Yellowstone Lake is anything but quiet. And that's true. And we have hundreds of active hydrothermal vents. We have big and small hydrothermal domes that are currently forming. This North Basin hydrothermal dome is a dome in formation. We have landslides that are happening. We still have smaller explosions coming from Elliott's crater. We have faulting activity. If you look at any recent seismic map, any recent map of Yellowstone Lake's seismicity, it's a very active area. So, and then to the north, we have kind of the Sour Creek Dome, and then the Elephant Back Mountain and Mallard Lake Dome. And that area, especially, let's just keep it to Sour Creek Dome, it's inflating and it's deflating on a pretty kind of semi-regular basis. Norris Basin is also inflating and deflating, and there seems to be a relationship that when the inflation is occurring at Sour Creek Dome, deflation is occurring at Norris Basin. And then conversely, when inflation is happening at Norris Geyser Basin, you have deflation at Sour Creek Dome. And you can imagine what this does to the lake level. And it's like a bathtub. So, you know, when it's uplifting or inflating, water in the lake is pushed back to the southern part of the lake. And I think Bob Smith actually recognized this back in, I don't know, the 60s or so. And Peel and Molly Islands were getting covered with submerged. And then, you know, they emerged. So there's this rocking back and forth of the lake, but it's not due to the lake actually moving. It's due to the active deformation of the Yellowstone caldera.
Wow. So Lisa, the next two questions I'm going to combine because they're related, and they talk about something I think a lot of people were wondering and thinking about, and that is, this person says, did the major explosions at Mary's Bay and or Elliott affect aquatic life in the lake? In other words, did fish die? Did aquatic life die? And then related to that, there's a question as to when the cutthroat trout first appeared in Yellowstone. Would this have been after the last major, and this person says eruption, or I guess that's what they mean, eruption, not explosion.
Yeah, and we, for our purposes, so that people don't confuse volcanic eruptions with hydrothermal explosions, we call them explosions. There must have been a lot of change with respect to the biosphere in the lake when we had these explosions, especially the very large explosions. I am not a biologist and I have not studied this, but there must have been a lot of disruption. How much it was, I don't know. Was everybody wiped out? I don't know. Were there survivors? I don't know. We do have microbes that live and concentrate around the hydrothermal vents. So there's always life in the lake. So I don't think life was ever completely wiped out in the lake. And these microbial, there's extensive microbial mats around these hydrothermal vents, and they attract amphipods, and the amphipods attract the cutthroat, and the cutthroat attract the lake trout. And of course, the lake trout were much later introduced. One question I've wondered about, if you look at the large hydrothermal explosions around Yellowstone Lake and in Yellowstone Lake. The first one was 13,000 years ago, and that's really before people arrived on the scene. But the next one was 9.4 thousand years ago, and we know people were there. We know many different people lived around the lake and subsisted on the lake. And whether it be seasonally or what, people were there. And my question is, were people affected by these large hydrothermal explosions? Elliott's crater happened at 8,000 years ago. We know people were there during that time. Indian Pond was 2.9 thousand years ago. People were there. So how were the people affected? And certainly life in the lake affected by must have been affected somehow by the explosion craters, but that must have by the explosions of these explosion craters, but it must have also affected the people who were subsisting on resources of the lake. Anyway, that's something I really am interested in, and any archaeologist who wants to work with me on this, that would be great.
For sure. Here's another question. Were you able to track or notice the effects of the 1959 earthquake on craters and seismic activity, etc., in the lake?
No.
So, Lisa, the next two questions are very close to what you were just talking about prior. I'm going to kind of jump ahead and just one person makes the comment, we need to work on the archaeological aspects of all this, which I thought was great based on what you just said. Yeah. You agree. Maybe you were able to read the question. And the other one is probably the big question that everyone thinks about when they hear you speak, and that is, can we expect an explosion or some unusual event that will cause major damage? And this person says in the Northwest. And again, I think there's the volcanic, explosions. There's a hydrothermal, in volcanic eruptions and hydrothermal explosions. You're talking about hydrothermal explosions, but everyone I think is concerned about the possibility of major damage, or even maybe the ability to predict the next hydrothermal explosion.
Yeah, and that's what's really gotten us jazzed in this HDY Lake project is, when we first started looking at these hydrothermal explosions, we first had to characterize them, where they were they inside the caldera, outside of the caldera, along the Norris Mammoth tectonic corridor. We certainly have a few there. Where were they? How big are they? What do the deposits look like? The Yellowstone deposits are very different from those elsewhere in that they're so extensively altered. We're trying to learn how we can monitor hydrothermal explosions. We've gone great leaps in monitoring volcanic eruptions, but hydrothermal explosions are lesser well known, what actually triggers them. And that's why this study is so important. The fact that we identified two very different hydrothermal fluids in Yellowstone Lake is a very important one. And one of those hydrothermal fluids, the alkaline chloride fluids, those fluids we think are the ones that create these really big, destructive, large explosions. And so it's important, and the smaller vapor-dominated fluids, or I shouldn't say smaller, but we think, generate much smaller explosions that probably wouldn't hurt you too much. But these large hydrothermal explosions are of concern. And my question at the end, do thermal basins represent future homes or locations for hydrothermal explosions? It's an important question. And so I think it's very important. And I know the Yellowstone Volcano Observatory, which is a consortium of, I don't know, 7, 8, 9 different institutions, we're looking at this question as we speak. And so I think understanding the fluids, understanding the type of alteration, we were able to distinguish the mineralogy of the alteration associated with the vapor dominated systems and distinguish that from these larger mineralogy, or from the larger hydrothermal explosion craters that are dominated by the alkaline chloride fluids. So that was a huge leap in this paper.
Mhm.
Also, by looking and establishing this subaqueous hydrothermal explosion facies model, we're able to look at now at these deposits and determine, how did that deposit get in place? And was it just a fall deposit? Was it remobilized so this stuff moved across the floor of the lake? Were there landslides? One of the reasons we wanted to, back to this other question about activity in the lake, and landslides are very active. And if you have a large landslide versus a small landslide come into the lake, it could change the lake level. And a radical change in the lake level may trigger a hydrothermal explosion. You just need something to cause that rapid drop in pressure for the system to flash from liquids to steam, causing this rapid expansion of oops, did I just lose you? No.
Nope,
Oops, sorry.
you're there.
Sorry. So that's another trigger that you could have. And you could have seismic events that trigger the landslides. And in the case of Elliott's crater, we think the seismic event may have triggered a large mud slump on the eastern shore of Yellowstone Lake and help contribute to the failure of this hydrothermal dome with an impervious cap. So it's complicated, and there's a lot of factors that are involved, and no stone should go unturned.
Are there any other questions out there from anyone? I do have another question that we thought of here. Is the Lake Hotel Graben a threat to the hotel and development area?
Let's just say it's an active graben, and that there's been movement on that graben at least 3 times. We think it's a recently formed graben. It's an extension of the Eagle Bay fault system. I'm not going to make any comments here as to whether that graben is a threat to the development area around Lake Hotel. But I do know that a more recent event, probably about 2,000, maybe 3,000 years ago, maybe associated with the Indian Pond explosion, that resulted in a total displacement of about 3 meters in the graben, which is pretty significant. So I don't know, it's a question, it's a good question, and it's something we should be considering.
Thank you.
And, if you go into, before they did the remodeling in the Lake Hotel, and you looked at the old windows, you could see the panes and you could see their deformation, and go from perfect rectangles to, turned and distorted rectangles. And I thought that was kind of interesting. So I'm sure, and I've never done a real detailed tour of the hotel, but I'm sure there's fractures in the foundation and in the walls that are related to deformation of the caldera or the Lake Hotel Graben.
Okay.
Thank you, Lisa. Any
Well,
other questions?
Maybe we'll make this one the last one, because I'm sure, Lisa, you're getting tired from speaking for an hour and a half.
No, I'm glad people are interested.
Oh, yeah. So the last one is, does water temperature and pressure of depth help control possible explosions? So, okay. Water temperature and depth of the lake, how does that possibly control explosions?
So, if you think about depth, we know that 1 atmosphere of pressure is equal to about 10 meters. So in the deep hole, at about 119 meters depth, we have 12 atmospheres of pressure being applied to that system. We also know at the deep hole, we have temperatures that are as high as 174 degrees C. So it's actually the hottest water yet recorded in all of Yellowstone. And it lies at the bottom and in the deepest part of the lake. So I think the question was, is it related to, are explosions related to the depth? Well, if you can get the water off of the system by whichever means you can find, you're going to get an explosion. And if you keep the water on top of it, it will subdue it to a certain extent. And so if you go back to that LiDAR map and the lakeshore terraces, you can add the depth of the, you can take the lakeshore terraces and the old lake levels and add that to the depth of the explosion craters. And Mary Bay was pretty deep, but when it had 14 meters of water washed off of it, it became pretty shallow, right? So, and Mary Bay is pretty hot. We've got some really hot vents in that area. So yeah, there's a relationship there, certainly.
Thank you so much, Lisa. This has been very interesting. We had some great questions tonight, and I just really appreciate all the hard work you've done at Yellowstone Lake and in Yellowstone National Park over the years. So thank you.
Well, I want to thank you for inviting me, and it's great to see Diane after many years, and we worked closely together. And I worked with you, Karen, when you were an interpreter at Yellowstone Lake in the day. Yeah. And I will just let people know if they have additional questions or would like a preprint of our paper that will be published pretty soon. I'm happy to send it. And my email address is lmorgan@usgs.gov. So LMORGAN@usgs.gov. And feel free to write me. And if you just want a copy of the paper, I'm happy to send that to you.
That's great.
Thank you, Lisa.
And thank you to everyone watching from home. We'll see you next week for a program about art in Yellowstone.
And thank you for watching
Yes,
and inviting
definitely.
me. This has been great.
You're welcome. Bye for
Thanks,
now,
Lisa.
Lisa. Thank you.
Take
Bye.
care.
Bye.
See you soon in Yellowstone.
You got it.